Hello and welcome to the final video in this series, number 20. And in this video I'll review some examples of solving inequalities that involve polynomials and rational expressions and absolute values. So in the last video we reviewed linear inequalities like this: 7x minus 4 less than or equal to 4x plus 5, and we solved this inequality and ended up with the solution that x less than or equal to 3, which we can also write in the form x is in the set in the interval between minus infinity and plus 3, not including minus infinity but including 3. But what if we have an inequality that involves, say, some squared terms? So for example, x squared plus 4x minus 3 less than or equal to 5x plus 9. So we want to solve this inequality, which means finding an interval or multiple intervals for x that satisfy this inequality, such that if we plug in any value of x in those intervals, the left-hand side would be less than or equal to the right-hand side. So we employ kind of a similar method when we're solving this kind of inequality, which in this case is quadratic, but you'll see that the end result is a little bit different. So in this case, what I want to do is I want to move everything onto one side of the inequality and just leave 0 on the other side. So a similar approach to the way we solved linear inequalities, but slightly different because I'm trying to get 0 on one side. So all I need to do is I need to subtract 5x and subtract 9 from both sides. So I'll have x squared and 4x minus 3 and then minus 5x minus 9. So now I've got 0 on one side, and now I just need to collect terms here. I've only got one x squared term. I've got a 5x minus 4x, so that's going to be minus x. And then I've got a minus 3 minus 9, so that's going to be minus 12. And then our instinct ought to be, whenever we see a quadratic like this, can we factor it? So two numbers that multiply to get minus 12 and add to get minus 1. So 4 and 3, one of them plus, one of them minus, should do that. And in this case we want a minus 1, so we'll need minus 4 and plus 3. So now that we've expressed the inequality in this form, and we know that this quadratic function represents a parabola that opens upwards, so it's more of a valley than a hill because there's a positive coefficient on the x squared plus 1. And so we know that the roots of this parabola are at 4 and minus 3. So that means the parabola crosses the horizontal axis at minus 3 and plus 4. Now we want to know where this quadratic function or quadratic equation is less than or equal to 0. In other words, we're interested in this part of the graph because that's where it's less than or equal to 0. So in other words, we've discovered that the solution set here is x in between. Let's do it like this. X is going to be in between minus 3 and 4. And this is less than or equal to signs because we've got a less than or equal to sign here. So it includes the two roots of the equation, minus 3 and 4. And in interval notation, we say that x is in the interval between minus 3 and 4. As usual, whenever we solve an inequality like this, it's good to see if, at least if we plug in a test value, that it does give the right result. So our test value could be, let's actually do 3 test values here. Let's do one on the left of this interval, so say minus 4. So x equal minus 4. And then we'll do one inside the interval. So let's say do x equal 1. That's a number inside this interval. And then let's do one on the right-hand side. Let's do x equal 5. And see what happens to the inequality that we started with, which was up here. So if I plug in minus 4 on the left-hand side, I'm going to have, let's see, 16 minus 16, minus 3. And we want that to be less than or equal to 5 times minus 4 be minus 20 plus 9. So we're going to have minus 3 on the left-hand side, and we're going to have minus 11 on the right-hand side. Minus 3 is not less than minus 11. So this statement is false. And for the value in between, the 1, we're going to have, let's see, 1, just write it down, 1 and 4 minus 3. We want that to be less than or equal to 5 plus 9. And on this side we've got 5 minus 3 got 2, and on this side we've got 14, so that's true. So we've got a true statement there. And then on the right side of the interval, if we pick 5, we have 25 and 20 minus 3, and we want that to be less than or equal to 25 and 9. And let's see, so we got 25 and 20, so 45 minus 2, so 42 on this side, and on this side we've got 34, so that's false. And this checks out because we wanted to find the values that satisfied the inequality, and we ended up with everything in between minus 3 and 4. So when we picked a value in between minus 3 and 4, everything checked out. When we picked 2 values that were not inside this interval, then the inequality did not work out. So this is kind of a nice way to check a quadratic inequality once you've solved it. Pick a couple of values outside the interval that you ended up with and see if the inequality doesn't work out, and then pick a value inside the interval that you ended up with and see if it does check out. So that's an example of a quadratic inequality. Let's look at an inequality involving a rational expression. So let's do x plus 2 and x minus 1. And let's see where this rational expression is greater than or equal to 0. So the approach with rational expressions is a little bit different. It's more of a just thinking things through. So first thing that I pay attention to when I'm looking at a rational expression is where it's not defined. So if x was 1, we would be trying to divide by 0, and we're not permitted to do that. So x equal 1, this is undefined. Another interesting value is x equal minus 2, because then this rational function is, or rational expression, is equal to 0. And we're trying to find when the expression is greater than or equal to 0. So we've found one solution, x equal minus 2. So we've got two kind of key values here. So the next step is to look at some test values that are in the intervals defined by these key values. So what I'm thinking about is if I've got a number line and I've got the value -2 and the value 1, then what I want to do for my test values is pick something on the left of -2, say -2, -3 is to the left of, sorry. Yes, that's right. So what we want to do is pick values in each of the intervals defined by this number line. So to the left of -2, so for example, -3, and then something in between -2 and 1, so say 0, and then something to the right of +1, so say 2. And see what the sign of the function is. So if we have x equal -3, then we would have -1 in the numerator, and we'd have -4 in the denominator, and that is a negative divided by a negative, so that's greater than 0. If we have 0 in place of x, we would have a positive. We would have 2 plus 2 in the numerator and -1 in the denominator, so that's going to be negative. And then if we have x equal 2, we'd have +4 in the numerator, and we'd have 1 in the denominator, and so that's a positive divided by a positive, so that's going to be positive. Now we're looking for where this rational expression is positive or 0. The only place where it is 0 is at x equal -2, and it is positive here and here. So putting all these pieces together, remember we want to end up with a statement kind of like this one, for which this rational function is, in this case, greater than or equal to 0. And we've discovered that it works when we are on the left-hand side of -2, including -2. It doesn't work in between, and it works on the right-hand side, but not including the value 1, because at the value 1 the function is undefined. So x is either less than or equal to -2, or x is bigger than 1. And in interval notation, the way we write that is x belongs to the interval between -∞ and -2, including the value -2, or, and in set notation we denote or using the union symbol here, or the interval between 1 and infinity, and we're not including the value 1. So dealing with rational expressions, it's steps. You just go through the steps thinking about key values and thinking about test values defined by the intervals that are set up by those key values. Let's move to an example involving absolute values. So let's do 2x minus 3 absolute value less than 5. So we want to find all values of x that satisfy that inequality. So if we think about what this means, it means that 2x minus 3 as a number must be in between -5 and +5. This continued inequality is another way of writing this inequality here with the absolute value. And so now we've already seen how to solve this kind of example. We did an example like this in the last video, but I'll just run through the steps real quick. Let's add 3 first of all. So minus 5 plus 3 would be minus 2. And then 5 plus 3 would be 8. And then divide through by 2. We'd have minus 1 less than x less than 4. In other words, x is in the interval between minus 1 and 4. And we could check, say with the value 1. 2 times 1 is 2, minus 3, minus 1, take the absolute value of minus 1, we get plus 1, and plus 1 is less than 5. So we've got some reassurance that we've done this correctly. Let's do another type of example with an absolute value in it. Let's do 4x minus 6 greater than 2. So thinking about what this means, it means that the number represented by 4x minus 2 is either less than minus 2 or 4x minus 6 is greater than plus 2. Because then when we take the absolute value of it, the absolute value would be greater than 2 if either of these conditions holds. So we have 2 inequalities to work with, 2 linear inequalities. So we just have to work both of them. So this one first, involving the negative 2. So let's add 6 to both sides. So minus 2 plus 6 would be 4. So this one is x less than 1. And then the other one is to add 6 to both sides. So we've got 4x greater than 2 plus 6 would be 8. So x greater than 2. And in interval notation, that would be x is in the interval between minus infinity and 1, or, so we use our union notation, or the interval between 2 and plus infinity. And again, we could check with numbers in either one of these intervals and check that our original inequality works. So for example, something that's in between, in this interval here, say 0 is in this one. So we would have the absolute value of minus 6, which is plus 6, and 6 is greater than 2, so that works out. In this interval, we could pick the number 3. 4 times 3 is 12. 12 minus 6 is 6. Absolute value of 6 is 6, and 6 is bigger than 2. So both of those numbers work out. So at this point in the video, I'm going to put a couple more problems up and pause the video and work through those 2 inequalities that I'll put up in a second and see if you can solve them. In other words, find values of x that will satisfy the following 2 inequalities. So the first one, let's do a quadratic, so kind of like this one. Let's do 5x squared plus 2x minus 5 greater than x squared plus 2x plus 4. And then let's do an example involving a absolute value. Let's do absolute value of minus 3x plus 6. And let's have that be less than or equal to 9. Okay, so let's see how you did on the quadratic inequality first. So I want to move all the terms over to one side and leave 0 on the other side. So I'll have 5x minus x squared, so I'll have 4x squared. And then I'll have 2x minus 2x, so that the x term actually goes away. And then we'll have minus 5 minus 4, so minus 9. And hopefully when you got to this point you recognized that this was a difference of squares. So that should make you think about conjugates. So we're going to have 2x plus 3 times 2x minus 3. If we multiply this out, we get 4x squared minus 9, and then 6x minus 6x, so that cancels. And so x, the roots of this are at x, so the roots are at x equals minus 3 over 2 and plus 3 over 2. So the only thing that's left for us to do is just to think about what this would look like if we draw it on a graph as a parabola. So it's we've got a positive coefficient on the x squared, so that means it's going to be opening upwards rather than opening downwards, and more like a valley than a hill. The roots are at minus 3 over 2 and plus 3 over 2. So here and here. And we're trying to find where this quadratic is greater than 0. So the part of the function that we're interested in is actually this piece and this piece. So which is different to what we did before, where we looked at in between. In this one, we're looking at outside. So if I write down my intervals, and I've got a strict inequality here. It says greater than 0, not greater than or equal to 0. So these two roots are not going to be included in my solution set. So we want x less than minus 3 over 2 or x bigger than plus 3 over 2. And in interval notation, that's going to be x is in the interval between minus infinity and minus 3 over 2, union 3 over 2 to plus infinity. Okay, so that's the solution for the quadratic example, and then let's do the solution for the absolute value example. So this absolute value inequality means that this value, minus 3x plus 6, is in between minus 9 and plus 9. And then if I subtract 6 from all three pieces, I'm going to have minus 15 on this side, minus 3x in the middle, and I'm subtracting 6, so I'll have 3 on that side. And then I'll divide all through by minus 3, so I'll have minus 5. And because I'm dividing by a negative number, I have to switch the direction of the inequalities. And sorry, I'm dividing by minus 3, so I'll get plus 5. So x. And then 3 divided by minus 3, so minus 1. And then I'll just switch this around so it's in the conventional direction. So x in between minus 1 and 5, including both endpoints. So in interval notation, that would be x is in the interval between minus 1 and plus 5. So that's it for this video, and this being the last video, that's it for the entire video series. So I hope you found these videos useful.